Okay, we're on the second section, instantaneous velocity and speed. This is a short section, so I may just continue on with the following one. Instantaneous velocity and speed. We did a little exercise where we took the slope of the line from A to B, and we got an average velocity from A to B. We could do the same thing from A to F, and we would get um, a different average velocity or average speed, depending if you're not concerned about the direction. But you can notice that the slope from A to B is positive, and the slope from A to F is negative. So that would be like a negative speed, because if you recall, the car went forward and then it went backward, and overall you would get a negative velocity if you do it that way. But now let's just focus on that area from A to B, and you should be familiar with this. Uh, if you've studied calculus, if you keep moving that blue line, they still show the initial b. If you move the b back further and further and further, you would approach the green line, which is the instantaneous velocity. So as you decrease the delta t, now notice that the t is on the horizontal axis. As you decrease the t, the instantaneous velocity is the limit of delta x over delta t as delta t approaches zero. So we're looking at the limit of delta t. The limit of delta x over delta t as delta t approaches zero, and you will get the slope of the line at that point, which is the derivative. It's the derivative of that point. Okay, so that's dx dt, the derivative. Okay, members of the Highway Patrol are more interested in your average speed or your instantaneous speed as you drive. There's no way to measure your average speed, but they can take an instantaneous shot with a radar gun, and so they're interested in your instantaneous speed. Now, because this has been so short, I'm going to continue on with the next section, the analysis model, particle under constant velocity. Constant velocity, there's a lot of things we can do, just as we can do its constant acceleration. So the analysis model here under constant velocity represents the common situation when solving physics problems. Okay, so the average velocity is delta x over delta t. That's what it's defined as. So Vx is equal to delta x over delta t. Now let's expand that. Delta x is x final minus x initial. So Vx is equal to x final minus x initial divided by delta t. Now, so if we solve for x final, we see that the Vx times delta t leaves you with x final minus x initial. And if we add x initial to each side, we'll end up with x final equals x initial plus Vx delta t. What does that mean? It means that if we have a constant velocity, now this is only true for a constant velocity situation, we start off with some initial position. In a lot of cases, that position is zero, but we come up with an initial position, x initial, and whatever the constant velocity is, we multiply that times the time. So your velocity might be something meters per second times seconds. What's it going to give you? It's going to be meters. So we have meters plus meters will give you the final distance in meters. So x final equals x initial plus Vx t for a constant velocity x, Vx. Okay? Now, so Vx equals delta x over delta t, x final equals x initial plus Vxt, and it looks like a straight line. The delta x over delta t is a straight line, and so that's your velocity. It's meters per second. If you have, well, it could be miles per hour, but most of what we'll use is meters per second. So x equals x initial plus v initial times t. That's for constant velocity. If you have a varying velocity, this is not going to work. And we'll get into a situation where the velocity is varying, and we'll handle that in different situations in a different way. Okay, now if it's under constant speed, the velocity is equal to distance divided by delta t. So an example, if you're going around a circle, let's say you're on a circular track, and the circumference of a circle is 2 pi r. So if velocity equals distance over delta t, we get that delta t is equal to d divided by v. So the circumference of if the radius of a circle is 10 meters, then and your constant speed is 5 meters per second, then you'll 2 pi r. The 2 pi is about 62.8 or thereabouts time. I mean, 2 pi is 6.28 times 10 is 62.8 divided by 5 meters per second gives you about 12.6 seconds. It'll take you 12.6 seconds to go around the circumference of a circle of 10 meters in radius. Okay, particle under constant velocity. You can see the particle is shown as this pink ball, and you'll see that the velocity is the same at each position. If you were to measure it, you would see that it would be the same length in each of those, and we'll see that when we get to motion diagrams. We'll use this concept in motion diagrams of the varying velocity vector. This velocity is a vector. So the constant velocity Vx equals delta x over delta t. The position as a function of time, we've said it before, x final equals x initial plus Vx times t, the elapsed time. Okay, particle under constant speed, if it's varying, you have the velocity is equal to the distance over the delta t. There's a total distance. You can't just go from the initial position to the final position, because the position between the first the red ball and the final red ball is shorter than the sinusoidal path that it takes. So there, the constant speed is the distance you've traveled over delta t. You can't use a position vector, just the distance traveled. Okay, and I'm not going to cover analysis, the problem-solving approach. You should read that. I don't necessarily go through this, but you might find it helpful to conceptualize what you're doing, categorize it as a problem with constant velocity, or categorize it as a problem with constant acceleration. Those will give you two different types of solutions. Analyze it, and then finalize it. Analyze the problem, use the proper equations, and finalize it. And I think that's where, let's see, analysis 17 to 23. Let's see. Yeah, that's all I want to do. We'll get into acceleration in the next one. All right, that's it for this one.